In January of this year, a team of astronomers published a paper confirming that the James Webb Space Telescope had detected a galaxy that existed just 280 million years after the Big Bang. The universe is 13.8 billion years old. This galaxy was already there when the cosmos was barely 2% of its current age. It was not supposed to exist. Not at that distance, not at that brightness, not with those chemical signatures. The lead author, Rohan Naidu, and his colleagues titled their paper A Cosmic Miracle. They were not being dramatic. They were describing what the standard model of cosmology would require to produce an object this luminous this early. And that galaxy, designated MOM-Z14, is not an isolated anomaly. It is the latest in a pattern that has been building since Webb opened its infrared eyes in 2022. A pattern of objects in the early universe that are too bright, too massive, too chemically mature, and too structurally organized for the timeline our models say they should have formed in. In 3 years of science operations, Webb has broken the record for the most distant confirmed galaxy 3 separate times. It has discovered the most distant supermassive black hole ever found. It has detected light that was not supposed to escape the dense fog of the early universe at all, and it has forced the scientific community into a position that one of the researchers working with its data described in terms that are hard to misinterpret. Something real is happening. But we cannot tell yet if it is a mistake in our observations, a mistake in our interpretation, or just something nature is surprising us with. Stay with me, because this is the story of what the most powerful telescope ever built found when it looked back to the beginning of time, and why what it saw does not match the universe we thought we understood. To make sense of why these discoveries matter, you need to understand what was supposed to be there, and what was supposed to be there was nothing. After the Big Bang, the universe went through a period that astronomers call the Dark Ages. For roughly the first 200 to 400 million years, there were no stars, no galaxies, no light sources of any kind. The cosmos was filled with clouds of neutral hydrogen gas so thick and so pervasive that even if something had been glowing inside them, the light could not have escaped. Neutral hydrogen is essentially opaque to ultraviolet radiation. Any photon emitted at the right frequency would be absorbed almost immediately by the surrounding gas. The universe was a fog. Not metaphorically, physically, a dense, light-blocking fog that extended in every direction. Whatever was happening inside it was invisible. The Dark Ages ended when the first stars ignited and began pouring out enough ultraviolet radiation to ionize the surrounding hydrogen, stripping electrons from the atoms and turning the opaque neutral gas into transparent ionized plasma. This process is called cosmic reionization, and it did not happen all at once. It happened in patches. The first stars and galaxies carved out bubbles of ionized gas around themselves like clearings in a forest. Over hundreds of millions of years, those bubbles grew and merged until the entire universe became transparent. The conventional understanding was that this process began in earnest around 400 million years after the Big Bang and was mostly complete by about 1 billion years. Galaxies were not expected to exist in significant numbers before that process was well underway. Webb found them anyway. The current most distant confirmed galaxy is MOM-Z14 at a redshift of 14.44. Redshift is how astronomers measure cosmic distance. The higher the number, the farther back in time you are looking. At redshift 14.44, the light from MOM-Z14 has been traveling for approximately 13.5 billion years. We are seeing it as it existed just 280 million years after the Big Bang, deep inside the Dark Ages, at a point in cosmic history when the standard models say large luminous galaxies simply should not yet exist. The previous record holder was JADES-GS-Z14-0, confirmed in 2024 at redshift 14.32, visible as it was 290 million years after the Big Bang. Before that, JADES-GS-Z13-0 held the record at redshift 13.2, about 325 million years after the Big Bang. Each discovery pushed the frontier earlier. Each one was more luminous or more chemically complex than models predicted for that epoch. Peter van Dokkum, a Yale professor of astronomy and physics and co-author on the MOM-Z14 study, said directly that while they were hoping for some very early objects, he did not think any of them expected to break the redshift record. If you are the kind of person who stays for the real science, drop a like right now because it genuinely helps this kind of content reach more people who want to hear it. But the distance record is not what makes these galaxies genuinely unsettling. It is what they look like when you examine them closely. JADES-GS-Z14-0 is not a faint smudge. It was surprisingly bright. Its light was dominated by stars, not by a central black hole. It showed signs of oxygen emission, a heavy element that is forged inside stars and scattered when those stars die. Oxygen appearing in a galaxy 290 million years after the Big Bang means stars had already lived and died there, multiple generations of them fast enough to enrich the surrounding gas with heavy elements in a time frame that pushes the models to their limits. MOM-Z14 showed something similar. Its spectrum revealed a high nitrogen to carbon ratio and chemical similarities to extremely ancient stellar populations, consistent with an early and intense burst of star formation. Naidu and his colleagues wrote that JWST appears poised to drive a series of great expansions of the cosmic frontier. Previously unimaginable redshifts approaching the era of the very first stars no longer seem far away. And in March 2026, astronomers discovered EGS-Z11-RO, the most distant red galaxy ever found, at redshift 11.45. Red galaxies are significant because their color comes from dust. Dust requires multiple generations of stars to produce. Finding a dusty red galaxy less than 400 million years after the Big Bang adds another layer to the same problem. The early universe was assembling structure, building stars, generating dust, and enriching its gas with heavy elements faster than any model had predicted. Then there are the black holes. GN-Z11, a galaxy first spotted by Hubble and later studied in detail by Webb, lies roughly 13.2 billion light-years away. Webb revealed a supermassive black hole at its center, making it the most distant black hole on record, formed just 400 million years after the Big Bang. The problem is not that a black hole existed that early, the problem is its size. Supermassive black holes are built either from the deaths of the first massive stars or from the mergers of smaller black holes over time. Neither mechanism, as currently understood, produces black holes this large this quickly. The standard growth models do not have enough time. Some researchers have proposed that the first generation of stars may have been far more massive than those we see today, collapsing directly into heavier seed black holes that could grow faster. Others have suggested that black holes in the early universe may have been able to accrete material at rates exceeding what was previously thought physically possible. In May 2026, a NASA study led by Katrina Chwarovsky found that some of the apparently overmassive early galaxies Webb had detected were being brightened by hidden black holes at their centers, making the galaxies appear more massive than they actually were. That solved part of the puzzle, but the same month, a separate analysis from Leiden Observatory argued that other early galaxies might actually be even more massive than initial estimates, because a large fraction of their stars are too faint to detect directly. The picture is not converging on a clean answer, it is getting more complicated. Now here is the discovery that ties all of this together, and that genuinely changed the timeline of when the Dark Ages ended. In March 2025, a paper published in the journal Nature reported the detection of Lyman-alpha emission at redshift 13 from a galaxy called JADES-GS-Z13-1-LA. Lyman-alpha is a specific wavelength of ultraviolet light emitted by hydrogen atoms when electrons drop from one energy level to another. It is one of the strongest emission lines galaxies produce, and during the Dark Ages it should have been completely blocked. Neutral hydrogen absorbs Lyman-alpha photons with extraordinary efficiency. The fact that this emission was detected at redshift 13, just 330 million years after the Big Bang, means the neutral hydrogen between that galaxy and us was not completely opaque. Something had already carved a pathway through the fog. The mechanism turns out to be exactly what theorists had predicted but had never directly observed at this depth. The first stars and galaxies did not just sit passively inside the neutral hydrogen, they attacked it. Their ultraviolet radiation ionized the surrounding gas, creating expanding bubbles of transparent plasma around each source. Inside those bubbles, Lyman-alpha photons could travel freely. If the bubble was large enough and oriented toward us, the emission could escape and eventually reach Webb's instruments billions of years later. The detection at redshift 13 is the earliest direct evidence of this process in action. It tells researchers that reionization had already begun in earnest within the first 330 million years, earlier than many models assumed. The Dark Ages were shorter than we thought, and the galaxies that ended them were more powerful than we expected. Here is what I want you to take away from all of this. In 3 years of science operations, the James Webb Space Telescope has broken the record for the most distant confirmed galaxy 3 times. It has discovered galaxies, black holes, dust, heavy elements, and ionized bubbles at distances and timescales that push the standard model of cosmology to its limits. The early universe, according to Webb, was already grown up. Stars were forming, dying, and enriching their surroundings with heavy elements within the first 300 million years. Black holes were reaching supermassive scales in a fraction of the time the models said they needed. And the fog of the Dark Ages was being burned away from the inside by sources powerful enough to carve transparent tunnels through the densest neutral hydrogen in the history of the cosmos. None of this individually breaks the standard model. Cosmologists have been adjusting parameters, proposing new formation mechanisms, and refining their understanding of early star formation in response to each new finding. But the adjustments keep going in the same direction. The early universe was more active, more structured, and more chemically complex than the models predicted. And every fix that addresses one problem at the earliest times tends to create tension with something else further along the timeline. The Hubble tension, the stubborn 9% disagreement between two methods of measuring the expansion rate of the universe, remains unresolved. In April 2025, Scientific American called it a crisis. The DESI survey has found 3.5 sigma evidence that dark energy may be evolving over time rather than behaving as a constant. And on August 30th of this year, NASA's Roman Space Telescope launches with a field of view 200 times wider than Hubble's, designed specifically to survey hundreds of millions of galaxies and map the expansion history of the cosmos with precision no instrument has ever achieved. The standard cosmological model Lambda CDM is still the best framework we have. It explains an extraordinary amount of what we observe, but the edges are fraying, and the edges are where new physics has always lived. Webb has not destroyed the model. It has done something more interesting. It has shown that the universe we thought we understood was simpler than the universe that actually exists. And every time we build a more powerful instrument and point it at the oldest light in existence, the picture gets stranger. The question is not whether the textbooks will be rewritten. The question is how much. If this kind of deep, research-grounded science is what you come here for, subscribe right now and turn on notifications. Webb is still breaking records. Roman launches in 6 weeks. Ruben is already scanning the sky. When the next round of data arrives, you are going to want to have already understood what you are watching. Drop a comment with what surprised you most, and share this with someone who needs to hear it. Thanks for watching, and I will see you in the next one.